we're talking about complex numbers in the complex plane, we can visualize and kind of graph and connect our ideas of vectors that we did in the last chapter with the complex numbers as we know it. If I'm looking at a complex number and I want to visualize it in the complex plane, we have the real numbers along what is usually the x-axis in the horizontal direction, and our imaginary numbers go vertically. So if we have the complex number 2 plus 3i, it would correspond with the point 2, 3 on our graph. And if we wanted to talk about the number minus 4 minus 2i, we could say, well, that corresponds with a negative 4 in the real direction and a negative 2 in the imaginary direction. And there's really no difference here how we'd plot a point than there is with the x's and y's. Now, if we talk about the complex number, we give it a name z. There are some things we can do with it. We can talk about the absolute value of z. And the absolute value of a complex number in general is the square root of the real part squared plus the imaginary part squared. So we would say the absolute value of z is the square root of 13. If, I don't know what to call this one, we'll just call it a, I guess. The absolute value of a is going to be the square root of negative 4 squared plus negative 2 squared. And when we square negative numbers, we get positive values. And so the absolute value of negative 4 minus 2i is 2 times the square root of 5. When we're drawing and looking in the complex plane, we can think of this as like our vectors that we worked with in the last chapter. And so your author will write z as a vector in component form as 2, 3. So there's my vector z. My vector a, negative 4, negative 2, means from the origin I've gone left 4 and down 2, and we pretend that line's straight when we draw it. So if I want to take z plus u, for example, okay, in my crazy not straight line, I said u, but I mean a. Okay, if this is z and this is a, if I want to take z plus a, I would get this resultant vector here. Good grief, my aim is terribly off today. Closer to that. Which looks like it would be left 2 and up 1. Now the nice thing, and your author is going to draw lots of pictures, it's going to draw them with vectors much nicer than I can. But if I wanted to add two complex numbers together, okay, we already did that in the last video in our super fast algebra review. And we said we're going to add the real components together. We're going to add the imaginary components together. And we get the number negative 2 plus I. Okay, or in vector form, it's negative 2, comma 1. If I wanted to subtract, and again, your author will help you visualize that with some pictures, but I know that if this is A, if I wanted to subtract A, oops. Okay, so I honestly don't remember what I was saying before I paused the video because I just took a really long phone call. So I noticed that I was adding here, and if we wanted to subtract, it would work the same way. I do know that I mentioned our book Draw Some Great Pictures of the Vectors, and I I'm not super good at that, so I'm gonna let you look there because I feel like it's pretty, I'd say easy to follow, but I do think they do a good job of drawing those pictures. Okay, so addition and subtraction of complex numbers algebraically works the same. The author will say, add these numbers in the complex plane, and it just means do what we did in the college algebra review. Now, if I want to talk about complex conjugates of two numbers. I know that the complex conjugate of 2 plus 3i is going to be 2 minus 3i, as I write off the end of my page. And so 2 plus 3i is up here, and 2 minus 3i is down here. And so these 2 points are a reflection across our real axis. So if I was back here at this complex number, 1, 2, 3, 4, 5, 6, 7, looks like negative 7 plus 1i. If we wanted to talk about its complex conjugate, we just reflect it across the real axis. The real portion of that number is the same, and the complex pieces are opposites. Okay. Now, maybe I want to find the distance between two complex numbers. The nice thing about our formula is that the distance formula is the same as it was if we're in the real plane with our x's and our y's. We're going to take the difference in the real values and square it. We're going to take the difference of the complex values and square it. Okay, or the equivalent of the difference of the x's and the difference of the y's. And remember, the distance formula comes from Pythagorean theorem. So it's a squared plus b squared equals c squared. If that were to simplify, we'd break it down more. I think we're pretty safe to say that's done. If we want the midpoint of the line segment, midpoint formula is we're going to add up the x components of those vectors, all right, plus a negative 7, so you know I'm adding, and divide by 2. We're going to add up the y components, or the imaginary components, sorry, and divide by 2. So the midpoint is negative 5/2, 1, which if we go to its corresponding complex number, that's negative 5/2 plus 1i, or in vector form, it's negative 5/2, comma 1. But the formulas correspond very exactly with, instead of x's and y's, we're going to put the real component and the imaginary component with a's and b's. But the difference in the first component squared plus difference in the y component, second component squared, and the square root of that is our distance formula. Midpoint formula is here. Overall, if you have any questions about what the book says, or about, this is again a college algebra review sort of thing, only we're using I's instead of other letters, please get a hold of me and I'd be glad to help clear it up.